Okay, so we will continue with stream ciphers. So, in the last day's class we had discussed about the Baldaccham-Massey algorithm, and the reason why we discussed was to point out the fact that a single LFSR system or a single LFSR based stream cipher is not adequate to prevent attacks of the type of for example, known plain text attack or chosen plain text attack. So, from the streams you are able to generate back the input seed of your LFSR based system, and from there the stream pattern is quite predictable in that fashion, right. So, although LFSR based stream ciphers were quite good because they were amenable to easy efficient hardware implementations, they had good proper statistical properties, the sequences had good statistical properties, but the patterns were quite predictable. Okay. So, we need to do something different, and in that pursuit in today's class we will see nonlinear feedback shift registers, and we will also see stream ciphers using more than one LFSRs, that is using multi LFSR systems. Okay. So, under that topic we will discuss about nonlinear combination generators, nonlinear filter generators, something which is called a clock control generator, and we will also just point out that there are some other stream ciphers which are actually not LFSR based. Okay. So, therefore, there are modern proposals which are not based on LFSRs, okay, and they are also being quite followed, okay, studied at least. So, first of all we will start with nonlinear feedback shift registers. So, as the diagram says to you that it is exactly the same as that of a feedback shift register which we have already seen, but only the difference is that in this case your feedback is nonlinear. Okay. So, in an LFSR our feedback was a linear algebraic equation. Okay. So, if you remember that this particular thing, that is, suppose you have got L stages in your LFSR or in your shift register, then the outputs or rather the contents of each of the delay elements are being taken as an input to your feedback polynomial, right. But in case of a nonlinear feedback shift register, this particular polynomial or this particular equation is nonlinear. So, we know what is the definition of a linear and nonlinear. So, it follows exactly, if I write this or describe this in the algebraic normal form or ANF form, then that means that this particular expression would encompass terms which are AND terms. Okay. So, they are not only based on XORs, but there are certain terms which are also AND based terms. Okay. So, a feedback shift register FSR is called a non-singular feedback shift register if and only if for whatever be the initial states of your FSR, okay, the sequences which this generates are periodic in nature. Okay. So, which means that there is a definite periodicity in the sequences which are being generated. Okay. So, in that case we say that this particular polynomial is a non-singular feedback shift register. Okay. So, you know that as we have studied that we need periodicity, okay, but the thing is that we also need to maintain or ensure that your periodicity is quite high, right, because small feedback small periodicity is not like because of possible attacks. Okay. So, therefore, we also need to ensure that although we are replacing this, so on one hand, in order to prevent the Baldaccham-Massey algorithm to work, we require our feedback polynomial to be a nonlinear equation. Okay. But at the same time, because of this nonlinearity, the easy analysis of the LFSRs are stopped, right. We cannot predict that it is periodic and things like that. So, therefore, even if we do even if we allow nonlinear terms into my feedback polynomial, I must also give guarantees of its periodicity, that is, the periodicity should be at least, for example, greater than so and so. Okay. So, we have to produce guarantees of that nature. Okay. So, therefore, we need to be little bit more careful, okay, because the analysis becomes harder compared to LFSRs which are quite easy to analyze. Okay. So, therefore, there is something which is called a Bruijn sequence. So, it is defined as follows: an FSR whose feedback function, that is f s j which operates on s j minus 1 to j minus l, okay, it is non-singular. So, we define what is meant by non-singularity. So, it means that the sequences which are being generated are periodic for whatever be the input seeds of your FSR. Okay. So, it is periodic, okay, it is non-singular if and only if f is of this particular form. So, what is the form? Now, f is equal to s j minus l XORed with whatever be some for any Boolean function g which operates on the remaining values. Okay. So, you see that S runs from j runs from the index of the inputs of g runs from S j minus 1 to S j minus L plus 1. Okay. So, this is a non singular, we can assume this particular fact, and the period of a non singular FSR with length L is at most 2 power L. Okay. So, therefore, the period of a non singular FSR with length L is at most 2 power L. So, therefore, the idea is that if you have for example, a 3-bit FSR which is of this nature, then the period can be at most 2 power 3, right, because there are at most there are 8 possible states. But for those particular generators for which the period is always equal to 2 power L is actually whatever be the initial state of your FSR are known as de Bruijn generators. Okay. So, that means a de Bruijn generator generates all the states or all the possible state values in its cycle. Okay. So, if you just compute the cyclic states, then all the possible 2 power L states lie in the cycle. Okay. So, therefore, this is the definition of a de Bruijn FSR, and the sequences which it generates are known as de Bruijn sequences. Okay. So, I think we saw one example of de Bruijn sequences. If you have really pondered upon that point which I have told you to ask to think upon, is that if you remember that a maximal length LFSR had generated, for example, a 4-bit maximal length LFSR had generated all 2 power 4 minus 1 non-zero values in one cycle. Okay. Only thing which was not in that cycle was the 4 0 states, that is the all 0 state. Okay. So, if you remember that this particular sequence which is generated, we have seen that the feedback polynomial in case of an LFSR was a maximal that polynomial was a primitive polynomial, right. So, and the sequences which is generated were actually something which was defined as M sequences. Okay. So, if you remember that I had given you one question that to think upon, how can you modify that particular LFSR structure so that the all 0 state is also included in the cycle. Okay. If you do that, it becomes a de Bruijn generator, right. So, therefore, you can actually take a maximal length LFSR and you can modify that. If you can solve that exercise, then you can modify that and produce something which is called a de Bruijn generator. Okay. And this is how you can do it. So, but before that, let us consider one example of a de Bruijn generator. So, it says that if consider this particular polynomial or equation which is called f x 1, x 2 and x 3, it operates upon x 1, x 2 and x 3, it is equal to 1 XORed with x 2, XORed with x 3, XORed with x 1, x 2. Okay. So, this is a very simple feedback polynomial which is being considered. So, if you start from 3 zeros, for example, you can work out this exercise and you can see that this 0 will get shifted here, this 0 will get shifted here, and this is 1. So, you can easily understand why it is 1, right. You can just feed these values here, all these are 0 and only 1 remains, right. So, therefore, this becomes 1. What about the next stage? This 1 gets shifted here, this 0 gets shifted here, and what is the feedback that you get? So, you see that the feedback here can be obtained by computing this particular value, and in this case x 2 is equal to so if I would I am trying to compute this value. So, x 2 is equal to 0, x 3 is equal to 0, x 1, x 2 is equal to 0. Okay. So, you get back 1. Okay. So, similarly, you can work out this will be also similarly you can see that it will be 1 XORed with x 2 which is 1, 1 XORed with 1 is 0. So, XORed with 0 is again 0, okay, and XORed with so x 1 x 2. Okay. So, you can just see, just work out this example. Okay. So, can you just find out what is the feedback value? This will be 1, right. 1 XORed with x 2 is 1 XOR with 1 is 0, XOR with 0 0, okay, and so x1 x2 is 1, so you get back 1, right. So similarly you can work out the remaining things also, and you will find that all the 8 states are actually lying in one cycle, okay. So therefore this is an example of a de Bruijn generator. So the idea that next we will consider is that given a say a 3-bit maximal length LFSR, I know how to produce a 3-bit maximal length LFSR, because in that case I just need my feedback polynomial to be primitive, right. So in that case I know how to produce a 3-bit maximal length LFSR. So how can I modify to obtain such a de Bruijn generator, okay. So this is how you can do it, and it is quite simple to follow. So therefore in order to convert, you see that let R1 be a maximal length LFSR of length L with linear feedback function f s j minus 1, s j minus 2 and so on till s j minus L, okay. So therefore this is an maximal length LFSR, okay. So therefore what is the meaning of that? That is a polynomial f should be a primitive polynomial, okay. So and you know what field it has to be primitive, okay. So therefore then the FSR, that is R2 with feedback function of G which operates upon the same input variables, okay, and if you define G to be in this fashion, that is it is nothing but f XORed with the knot of s j minus 1 ANDed with, so this is not comma, this is ANDed with s j minus 2, okay, ANDed with so on till s j minus L plus 1, that is if you just leave the last one out, okay, and you just take this and you XOR, then what you obtain is a de Bruijn FSR, okay. Can you understand why? So you note just one fact, I leave to you that to think the rest of the thing, you just work out a small example and check, that is if all the values, when does this XOR come into play? So except for the all 0 value, where is all these values are 0, this is nothing but the same feedback, right. So therefore you get back f. Only when this all of them becomes equal to 0, then you are essentially forcing back a 1, okay. So if you remember that in case of a maximal length LFSR, our problem was that the all 0 state essentially was feeding back 0, okay. But in this case you can observe that it will feed back a 1, okay, and therefore it will get back into the other thing, okay. So therefore this is nothing but a simple, you can state or pose this problem as a simple switching theory problem, right. So therefore it is just how do you get out of the wrong state, okay. So we have done simple examples like that previously also. So but this particular, so therefore if you solve that problem, therefore what you obtain is a de Bruijn FSR, because all the 2 power L values are now lying in one cycle, okay. And what is the difference from a maximal length LFSR? This particular polynomial or this particular feedback equation is no more linear, it is actually a non-linear thing, right. So therefore you have solved the non-linearity problem, at the same time you have ensured that periodicity is also quite high, right. Okay. So you can just take one small example and work it out also, okay. So now we will consider stream ciphers which are based on LFSRs, okay. So I mean the last example that we considered was not actually based on LFSR, it was a feedback shift register which was not linear, okay. But now we will consider stream ciphers which are based on LFSRs. Why do we like LFSRs? Because they are well suited for hardware implementations, okay. They have got large period, they have got good statistical properties. So however the key stream is quite predictable. So we have seen this, that the connection polynomial of an LFSR with linear complexity L can efficiently be computed from a subsequence of length 2L or more, okay. So therefore if you give a subsequence of length 2L, then you can actually compute the corresponding connection polynomial. You can also compute the linear complexity L by using the which algorithm? Baleka-Massey algorithm, okay, and you know the complexity of the algorithm is quadratic, right. So the subsequence can now we have also thought of this point that the subsequence, so therefore in order to recover we require the subsequence, and how can you obtain the subsequence? You can ascertain that by a known plain text kind of attack, Okay. So, if you know the plain text, if you know the corresponding stream cipher, then you can just XOR them and you can obtain the key stream, and if you obtain say at least 12 number of key stream values, from there you can regenerate or reconstruct the LFSR. Okay. So, therefore, we require more than one LFSR system stream ciphers, and this is how you can, we will just consider 3 types of such cases. We will consider using a nonlinear combining function on the outputs of several LFSRs. So, therefore, suppose there is not one LFSR, but there are more than one LFSRs, and all of them are producing a key stream, right. So, what we will try to do is that we will try to combine them using a nonlinear combining function. Okay. So, this is one example, one possible way. The other thing what we can do is that we can use a nonlinear filtering function on the contents of a single LFSR. So, I will explain more about details of this, and also what we can use is that we can use the output of one or more LFSR to control the clock of one or more LFSR. So, I will explain these possible constructions. Okay. So, first of all, let us consider this. Suppose there are n LFSRs and all these LFSRs are producing a key stream. Okay. So, what we do next is that we take a function f and we combine all of them and produce a key stream. Okay. So, note that here f is a nonlinear combining function, right. So, suppose that there is a result which states like this, that suppose that n maximal length LFSRs, so suppose that all of them are maximal length LFSRs, okay, and the lengths of all of them are say L1, L2 and so on till Ln, okay, where L1 to Ln are all mutually co-prime. Okay. So, what does mutually mean? So, are all pair yeah, and also they are pairwise distinct, right, you can follow from there. So, therefore, and if they are greater than 2 also, that means if you consider fairly large LFSRs for example. Okay. So, then you can actually predict that suppose if the corresponding nonlinear function f has got an ANF form. So, ANF form means an algebraic normal form. So, then suppose your suppose the form of f is f x1 x2 and so on till xn. So, this is the ANF form. Then actually you can predict the corresponding linear complexity of this particular key stream. How? Now, what you do is that you take this L1 to Ln and you feed in this function f, okay, and what you do is that you replace all the XORs by simple integer additions. Okay. So, if you do that, you can actually compute the corresponding linear complexity of the key stream. Okay. So, just let us consider one simple example. So, therefore, this is a something which is called a Geffe generator. So, just see that there are 3 LFSRs here, and this is producing one output, this is producing one output, this is producing one output, and this is the key stream. So, therefore, you can see that this is this particular, if I box this one, then this is my f, right. So, what is the form of f here? You take x1, you take x2 and you AND them. So, it is x1 x2 XORed with x3 x2 bar, right. So, the form would have been like this. You take x1 x2 and you XOR that with x2 bar x3. Okay. So, this would have been my form, right. So, therefore, this is my f x1 x2 and x3, right. So, I can write x1 x2 and I can write XOR, I can write 1 XORed x2 x3, and this is equal to x1 x2 XORed with x2 x3 XORed with x3. Okay. So, this is expressed in which form? In ANF form. Okay. So, now if the linear complexity of your LFSR 1 is L1, that of 2 is L2 and that of 3 is L3, and if all of them are not equal to each other and they are greater than 2, then the corresponding linear complexity of the corresponding Geffe generated stream would have been L equal to L1 L2 plus L2 L3 plus L3. So, here you note that these plus are integer additions, okay, and you are doing these operations over integers. Okay. and the periodicity of this particular Geffe generator also would have been equal to 2 to the power of L1 minus 1 multiplied by 2 to the power of L2 minus 1 into 2 to the power of L3 minus 1. Okay. So, these are guarantees that we can produce actually. Okay. So, but this Geffe generator is actually weak. Okay. So, why it is weak? So, you see that although it has got a good linear complexity, okay, and at the same time it has also got a reasonably good periodicity, I mean high value of periodicity, but still it is weak, okay, because of something which is called correlation attacks. Okay. So, why correlation attacks? Let us try to understand that. So, if you remember in your equation was x1 x2 XORed with x2 x3 and XORed with x3, right. So, you see that the Geffe generator is actually cryptographically weak because there is an information leakage of the output stream which is being generated and the value of LFSR 1 for example. Okay. So, LFSR 1 generates the stream which I denote by x1 and the output stream is suppose z. Okay. So, zt means at tth instance suppose z is being generated. Okay. So, now let us consider the probability or compute the probability that zt is actually equal to x1t. Okay. So, this you can follow from the equation. You see that if x2 is equal to 1, this is always true. You see that in your equation if x2 is equal to 1, then it is always true because you get x1, you get what? You get x1 XORed with x1 XORed with x3 XORed with x3. So, you see that x3 and x3 gets cancelled and you have x1. Okay. But let us say, what if your x1 is x2 is equal to 0? If x2 is equal to 0, then this vanishes and only x3 remains. Okay. So, therefore, this is I mean you get the intended result if x3 is equal to x1. Okay. So, therefore, you can write this equation, that is probability that zt is equal to x1t is equal to probability if x2 is equal to 1, and if x2 is equal to 0, then x3t is equal to x1t, right. And what is the probability of this? If you assume that your inputs are independently and randomly chosen, then your x2 is equal to 1 has a probability of half, okay, and x2 equal to 0 has a probability of half, and x3t equal to x1t is also half. Okay. And therefore, this probability works out to 3 by 4, right. So, therefore, this similarly you can show that zt is equal to x3t is also equal to 3 by 4. Okay. So, if you really want to generate a very strong cipher, an ideal value of this should have been equal to half, okay. But here it shows that there is a deviation from half, that is it is half plus 1 by 4. Okay. So, therefore, this deviation can be exploited actually by certain type of attacks which are called correlation attacks. Okay. So, how does correlation attacks work? So, what you do is that you assume for example, so if you just consider this single 3 LFSR system. Okay. So, therefore, what you do is that you assume the input value of for example, LFSR 1, okay, and then you consider the corresponding key stream which is being produced by the Geffe generator, right, and then what you do is that you assume this particular seed and compute the output of your LFSR 1. Okay. You find the number of coincidences between this value and the corresponding key stream, okay, and check whether it matches with the probability of 3 by 4. Okay. Then what you do is that instead of taking the corresponding output of the LFSR 1, you consider a shift of that. Okay. So, maybe a shift of 1 step. Now, check the coincidences. Okay. So, how many possible shifts are possible? That depends upon its periodicity. So, if its periodicity is 2 power L1, you can have at most 2 power of L1 such attempts, right. Out of them at least one you will get where this particular thing holds, right. You can repeat this effort for the other LFSRs also. Okay. So, therefore, if you engage an effort of 2 power L1 minus 1 plus 2 power of L2 minus 1 plus 2 power of L3 minus 1, because all of them are independent actually. So, then you should be able to recover the corresponding seed. Okay. But what was your ideal size of the seed for this Geffe generator? It was actually equal to 2 to the power of L1 minus 1 multiplied by 2 to the power of L2 minus 1 into 2 to the power of L3 minus 1. Okay. So, you see that although you have got a very large key size, expected large key size, you can actually reduce that to a much smaller value. Okay. And therefore, this Geffe generator is actually not a very strong stream cipher. Okay. So, therefore, for example, if you consider this example, that is, so this is a generalization. So, if you consider that n maximal LFSRs are there, so R1 to Rn and all of them have got length say L1 to Ln, then the number of keys should be actually 2 to the power of L1 minus 1 multiplied by 2 to the power of L2 minus 1, so on to 2 to the power of L1 Ln minus 1. But suppose you have got a correlation between the key stream and suppose the output of R1 with a probability of P which is significantly greater than half. Okay. So, what you do is that you guess the initial state of R1, compute the number of coincidences between the key stream and all possible shifts of the output sequence of R1 until you find that your probability is more than P. Okay. So, therefore, number of trials required would be at most 2 power of L1 minus 1, right, and since the initial states of the LFSRs can be known independently. So, total number of such trials will be sigma of 2 to the power of Li minus 1, where I runs for all the LFSRs. Okay. So, therefore, you see that this particular value is significantly smaller than this product term, okay, and therefore, you have an attack, right. So, therefore, what I would like is that what we would like is to make the Boolean function something which is called correlation immune, okay, and that gives you the definition of correlation immunity. Okay. So, what is correlation immunity? So, correlation immunity is again a criteria, like we have seen nonlinearity, we have seen some other things like balancedness, okay, degree. So, now we have another parameter which we also need to keep in mind, it is called correlation immunity. Okay. So, correlation immunity says like this, suppose you have got x1 to xn as your independent binary variables. Okay. So, consider for example, our 3 LFSR system. Okay. So, how many inputs are there for your f function? There are 3 inputs, right. There are 3 LFSRs, all of them are producing some output. Okay. So, if you understand that why the attack worked because the output of the LFSR 1 was actually leaking some information into the output stream. Okay. So, if I want a correlation immunity, what I would like to do is that the mutual information between the output of the LFSR 1 and the output stream should be actually 0, right. That is the objective. Okay. And how we can do that? If you understand, okay, first of all let us study the definition. It says that let x1 to xn be independent binary variables, each taking values say 0 or 1 with a probability of half. Then a Boolean function f is actually called mth order correlation immune if for each subset of m random variables, that is xi1, x2, xi2 to xim, the random variable which you obtain z is actually statistically independent of the random vector xi1 to xim, right. So, this is what I intend to do, right. So, therefore, I can state this in the fact that the mutual information of this vector and the corresponding z random variable should be equal to 0, right. So, if you remember the definition of mutual information which we have done in our Shannon's theory class, then you can understand how to do that. Okay. So, one way of doing this is, or rather one way of ensuring this is that if you take any Boolean function f, okay, and out of them xi1 to xim are some random variables. Okay. So, what I would like to do is that I have to give a proof that if I want an mth order correlation immunity for f, then I have to give a proof that if I fix xi1 to xim to some constant value, then the remaining function which I obtain as f should still be balanced. Okay. If it is balanced, then actually it is not leaking any information, but if it is not balanced, then it is leaking some information. Okay. So, if you remember your Boolean equation x1 x2 XOR x2 x3 XOR x3 which we had, okay. In that case, if we had, so if you follow this, that is, if in the equation say x1 x2 XOR with x2 x3 XOR with x3, okay. So, if in this equation we had held the value of say x1 to a constant value, then what is the remaining thing I get? If I, for example, if I make x1 equal to 1, okay, or if I make x2 equal to 1, I get f x1, x2 and x3 is equal to x1. So, you see that x1 is a balanced equation. Okay. You know, you see that x1 is balanced. Why balanced? Because if I obtain a truth table, then there are equal number of zeros and ones. Okay. Now, you see that actually you have to do this process for all possible things, right. So, therefore, all possible subsets. So, we have considered only x2 being equal to 1. So, what if x2 is equal to 0? So, if you see that x2 is equal to 0, we have considered x2 is equal to 0, right. This was for x2 is equal to 0. What if x2 is equal to 1? You obtain f of x1, x2 and x3 is equal to, if x2 is 1, you obtain x3, it is still balanced, right. So, now you consider that if, for example, x1 is equal to 1, okay. So, if your f is, if I consider that x1 is equal to 1, then what do you obtain? You obtain x2 XORed with x2 x3 XORed with x3, right. So, now you consider some other cases also, x1 equal to 0, okay. What do you get if x1 is equal to 0? Right, you get x2 x3 XORed with x3, right. So, what about this? You can write this as x3 x2 bar, right. So, you see that this is no more a balanced function, okay. This was a balanced function, or was it? I do not think this one was also not balanced, okay. So, yeah. Okay, so, having only one AND term does not mean that it will be actually unbalanced. Okay. So, for example, if you consider the function of this type, that is x1 XORed with x2 x3, then this is actually a balanced function. Okay. But yeah, but in this particular definition it is actually an unbalanced function. So, since this is an unbalanced function, you see that this particular function f is not correlation immune of 1. Okay. So, if you consider a simple example or simpler example, that is f x1 x2 x3 is equal to x1 XORed x2 XORed with x3, then this is actually correlation immune of order 2. Why? Because if you hold any two values here, you will find that you will obtain a balanced equation. Okay. See, for example, you fix x1, you fix x2, you have got x3. You fix x3 and you fix x1, you obtain x2. So, if you have a linear equation of n variables, then it is actually correlation immune of n minus 1, order n minus 1. Okay. But for nonlinear equations, it is not so simple. You have to do that thing. Okay. So, therefore, you see that if you really want that your function f should be able to protect against correlation immunity, I mean correlation attacks, then you have to guarantee that that function f is actually correlation immune for order m. Okay. This guarantee you have to produce. Okay. So, this is an example that we will follow of something which is called a summation generator, though this is an example, I mean a real life example. So, you see that there are n LFSRs, and what you do is that these streams that you obtain a simple integer sum. Okay. So, therefore, the integer sum will essentially produce a vector value of all these. If we add all these values, so all of them are ones and zeros. So, what you do is that you just do an integer addition, and the lower value you produce as a key stream. Okay. So, this is the LSB of your sum, and the remaining things you essentially feed back to your carry, okay, and this carry serves as a memory to your generator. Okay. In your next stage you also add this carry along with. Okay. In input you start with 0, and after that you keep on feeding back values into the carry. Okay. So, there are proofs actually which says that if the lengths L1 to Ln of the n LFSRs are actually pairwise prime, then your period of the key stream will be product of 2 power Li minus 1, and its linear complexity will also be close to this number. Okay. So, this is an example, and so therefore, there are more intricacies, we can go deep into this, but I am not going to this, but I just gave you as an example. Okay. So, therefore, so this is and there are some weaknesses also, but I will not go into them. Okay. But this essentially derives or is based upon the fact that your carry, okay, when you are doing an integer addition, your carry is actually a highly nonlinear term. Okay. So, you can take this as an exercise that for your ith stage of your integer addition, your carry is actually a Boolean function of 2i variables. Okay. And these 2i variables you can just try to see that what is the nonlinearity and what is the correlation immunity of the function. Okay. So, now we go into a second class of generators based on LFSRs. You have got n LFSRs, and this is, you see that this is nothing but a simple LFSR that we have seen. So, this output of these LFSRs, that is there are L stage LFSR, and these outputs are being combined by a Boolean function f, okay, and it produces a given a key stream, right. So, therefore, you see that in this case this f is nonlinear, okay, but your LFSR, that corresponding shift register is still based on a linear feedback. Okay. You are taking all these intermediate values and you are combining them by a function f. Okay. So, this is one way of solving this problem also. So, we will rather deeply little bit concentrate upon something which is called quite interesting, called clock control generators. There are two types of clock control generators, one which is called an alternating step generator. Okay. So, so what is the construction principle? So, there are essentially 3 LFSRs here. So, a control LFSR R1 is used to selectively step 2 other LFSRs R2 and R3. Okay. So, the output sequence is the XOR of R2 and R3. So, what you do is as follows: you take your register R1. So, therefore, this is the diagram. Okay. So, therefore, just concentrate on this diagram. You take the register R1, okay, and you clock this. If this register R1 produces a 1, then you take the output of register R2. Therefore, you see that this register R2 is clocked. Okay. But if this produces a 0, then you are not clocking this register. Okay. But what it produces here is the previous output value. Okay. And then you are taking an XOR of these two and producing the output. But if this value is 0, then this one is not clocked, but this particular LFSR is clocked. Okay. And when this is not clocked, this gives you the previous value, and you are taking the XOR and you are producing the output. Okay. So, this is the principle of and something is called an alternating clock generator, and there are results which says that if this particular R1 produces a de Bruijn sequence, you know what is a de Bruijn sequence. Therefore, this R1 produces a de Bruijn sequence, then the alternating step generator satisfies good properties. That means, it has got high period, it has got good linear complexity, and it is supposedly a very good stream cipher generator, okay, key generator. So, so there are consider concrete example of R1 being equal to 3 1 plus. So, you know this nomenclature, this way of noting, this is the length and this is the feedback polynomial. So, it is 1 plus d square plus d cube, and similarly R2 and R3 are as follows. So, you note that R2 and R5 R3 we have kept the feedback polynomial to be primitive. Okay. So, in that case this produces, so R2 is essentially a 4-bit LFSR. So, a maximal 4 bits LFSR means there should be 15 periodicity of 15, right. So, therefore, you see that R2 produces a periodicity of 15, R1 produces a periodicity of 7. Okay. So, is R1 a a de Bruijn generator? No, it's a simply it's a maximal length LFSR. Okay, and how can I produce how can I obtain the output key? So this is an, I mean you can just consider just think or reflect on this, that if this is the key stream which is being produced by a 3-bit maximal length LFSR, how can I obtain the output of a 3-bit de Bruijn generator? Okay. So, but I am not going into that. So, therefore, you can just think on this. This follows from the previous definition of de Bruijn generator that we have discussed. Okay. So, if you take R1 and if you take R2 and you know that, okay, you can also take and you take R3, then this is how you obtain Z. So, therefore, you see that if R1 produces a 1, then what you are supposed to do is that you are supposed to take R2 and R3 is initialized to 0. Okay. So, therefore, 1 XORed with 0 will give you a 1. Okay. Next, you see that there is a 0. So, if you get a 0, then you clock this one and you keep this one same. Okay. So, therefore, this was initially 1 and you have got a 1 here. So, 1 XORed with 1 is 0. So, you obtain a 0 here. Similarly, you can obtain the key stream. Okay, and you see that you have got a fairly large periodicity of the value. Okay, so therefore, this is a till now you have, I mean you do not see a periodicity here, right. So, therefore, this is a quite I mean this is a, you see a sequence being generated with a significantly large period. Okay. And another class of generators of this class, I mean is something which is called a shrinking generator. Okay. So, therefore, how it works is as follows: you take a control LFSR R1. So, therefore, again you consider this diagram. So, you take R1 and you take R2 and suppose that R1 produces a 1. If R1 produces a 1, then okay, so then if R1 produces a 1, then you take the output of R2 into the sequence. If R1 produces a 0, you drop this sequence. Do you follow? If R1 produces a 1, you take this sequence, I mean the output of we take Bi into your output, but if R1 produces a 0, then you drop the value of Pi. That means you do not take it. Okay. Therefore, you have to consider the next value of R1. So, you see that immediately the output sequence of Bi is being shrinked, because there are some values which you are dropping, right. So, therefore, you are so what you can state this in a different way, that is, if you consider LFSR R2, okay, and ensure that suppose R2 is a maximal length LFSR, okay, you arbitrarily drop some values from R2 depending upon the output of another LFSR, right. So, therefore, sometimes you drop and sometimes you do not drop, and therefore, this is how the construction of a shrinking generator works. Okay. So, there are results which says that if L1 and L2 are mutually co-prime and if the connection polynomials are unknown, then the security level is actually roughly equal to 2 power 2L. Okay. So, therefore, if you ensure that L is equal to 64, then this shrinking generator should be quite strong, because you know that it should give you a guarantee of 128 bits, and 2 power 128 is still quite high. I mean we are not giving guarantees of unconditional security, remember that we are giving guarantees of computational security only. Okay. So, this is another example. It says that R1 is equal to 3 1 plus d cube, R2 is this, initial states are so on. So, you can obtain this. Let us work out this example. You see that if R1 produces 0 here, then you know that you are if R1 produces 0, then you are dropping this value. Okay. So, next you again obtain a 0, you are not taking anything. Okay. You get a 1 here, then you are taking this. So, therefore, this 1 comes in the output. Okay. Next what you obtain is again a 1. So, therefore, you are taking this 0 is coming to the output. Okay. Next you again obtain a 1. So, you see that 1 comes, so this is 0, so again 0 comes here. Okay. After that you again obtain a 0, so which means you are dropping this value, next value, and again you have obtained a 1, so you are taking the next value into the output, this which is still 0. Okay. So, this is the way how you can obtain the output of a shrinking generator. Okay. So, I will just conclude with this slide, that it says that modern stream ciphers, I mean for modern stream ciphers can actually based on LFSR systems, non-LFSR systems also. Okay. And there are several proposals. There is actually a contest running on nowadays, which is supposedly trying to standardize something, some stream ciphers, like we have AES for block ciphers, right. So, there is a contest going on, and there is something which is called an eStream website, and there are hardware and software candidates which are mentioned in the eStream website. So, the search for standard stream ciphers continues while new attacks are also being developed. Okay. So, there are some attacks which are called algebraic attacks, there are some attacks called cube attacks which are quite powerful to analyze stream ciphers. Okay. And there are some new tests also which are being evolved, something which is called a demonomial test and so on. So, they are quite hard to, quite intricate to protect against, and stream cipher designs have therefore become all the more challenging. Okay. So, therefore, people are still searching for standard stream ciphers. You can just ponder upon this point. There is something which is called a self shrinking generator or SSG. What it does is as follows: it uses only one maximal length LFSR R. The output sequence of R is now partitioned into pairs of bits. So, therefore, consider one single LFSR, okay, R, and the output key stream you are partitioning into pairs. Okay. So, depending upon whether your pair is 1 0 or pair is 1 1, you are producing 0 or 1. If the pair is 0 0 and 0 1, then you are actually dropping. Okay. So, this SSG can actually be implemented as a shrinking generator and vice versa, that is a self shrinking generator you can implement using 2 LFSRs in the shrinking generator topology, and also vice versa. Okay. You can just try to work it out whether you can do it. Okay. So, I have followed Menezes' book, Menezes and Oatsworth and Vanstone's book on Handbook of Applied Cryptography. It is available online, so you can just go through this chapter also. Okay, chapter 6. So, next day's topic will be pseudo randomness.